Section 1.3, Key Ingredients of Deep Learning. Having gotten a taste of deep learning, we now discuss the key ingredients that leverage its success. These are notably the availability of large datasets, advances in computer architectures, advances in software, the internet, and the interplay of cognitive science and artificial intelligence. While the remainder of the book focuses on the mathematical description of deep learning, this section aims to overview the non-mathematical key ingredients which are attributed to the success of the field. Neural networks as artificial brains. Brains are composed of biological neurons that are interconnected in unstructured ways. See Figure 1.4, where display A illustrates a single biological neuron, and display C illustrates an interconnected network of biological neurons. Here's a figure. Look at A and C. A human brain has an estimated 85 billion neurons. A single human action, such as movement of an arm, may induce the firing of around 50 million such neurons. Whereas the identification of a visual object may use the bulk of the estimated 150 million neurons that are in the visual cortex. Unquestionably, brains are fascinating organs whose scientific understanding, while still at its infancy, will undoubtedly grow in the years to come and have profound effects on human endeavor. Deep neural network models are neither brains nor attempts to create artificial brains. Nevertheless, the development of these models is highly motivated by the biological structure of the brain. The basic building block of a deep neural network model is the artificial neuron, abstracting the synapse connection between neurons via a single number called an activation value. See display B of Figure 1.4 for a single artificial neuron, and display D, which presents a combination of multiple neurons into part of a feed-forward artificial neural network similar to Figure 1.3a. Pioneering and landmark work in AI research was inspired by neuroscience, since brains are essentially the only complete proof we have for the existence of what we call general intelligence. Further, many tasks of deep learning models involve the mimicking of human-level or animal-level tasks, such as understanding images or conversational tasks. Thus, for example, one of the most well-known benchmarks in the world for artificial intelligence is the Turing test, originally named the imitation game when introduced by Alan Turing in 1950. It is essentially a test to see if a computer can engage in long conversation with a human without another observing human distinguishing between the computer and the human. While advanced artificial language models are impressive, most experts would agree that to date, AI has not passed the Turing test. Similarly to the complete understanding of biological brains, the design of artificial general intelligence, AGI systems, is at best at infancy. Deep learning models generally only achieve narrow tasks, such as pattern recognition or playing specific games, as opposed to general intelligence tasks. With both the fields of neuroscience and AGI still awaiting major breakthroughs, it is natural for researchers to continue to draw parallels between neuroscience and artificial intelligence. On the cognitive sciences side of the spectrum, an increasing number of researchers are making use of artificial neural networks as abstractions for understanding cognitive tasks. However, on the AI side of the spectrum, while in the early years neuroscientific motivated models were central, today they have become more of a niche research area. In our context, the mathematical description of deep learning in this book is completely agnostic to biological brains. Computing power. It is well known that deep learning models require fast computers with plenty of memory. Training deep learning models can take hours or days using current state-of-the-art hardware and would not have been practically possible on machinery of the 1990s or earlier. Similarly, the large-scale application of trained deep learning models, such as, for example, in self-driving cars, requires massive resources, as it is tested by the fact that the power consumption for compute in a self-driving car can sometimes equate or exceed the power used by the engine. At around the first decade of the 21st century, a technological threshold was passed, and the availability of fast compute hardware made earlier deep learning ideas realizable and successful. A complete description of hardware advances and the relationship with deep learning is beyond our scope, and is not the focus of this book. Indeed, practical machine learning engineers often need to consider the computing power and hardware at play to train or implement effective deep learning models. A core component that has made a huge difference to the field is the development and availability of graphical processing units, GPUs. In contrast to standard central processing units, CPUs, which are optimized for logical operations, branching, and general computations, GPUs are optimized for repetitive large-scale matrix operations and can execute deep learning training or prediction in the order of 20 to 200 times faster than the state-of-the-art CPUs. The GPU industry initially grew due to demand from the video gaming market. However, by 2020, their importance in the AI revolution is well understood. Today, the needs of deep learning influence the design and development of future generation GPUs. In summary, it is fair to say that without GPUs, deep learning would not be anywhere where it is today. For example, the aforementioned success of the so-called AlexNet model in the 2012 ImageNet Challenge was based on a neural network model specifically designed to be trained on two parallel GPUs, which were the state-of-the-art of the time. From a programming perspective, utilizing such GPUs required considerable effort at the time, but since then has become much more accessible with better software. In the past decade, more specialized compute systems, including GPUs, the similar tensor processing units, and dedicated driver software, were specifically adapted for deep learning applications. Indeed, today, a machine learning engineer engaged in deep learning almost always needs to make use of such tools. Also central in this area is the availability of cloud computing. Today, many deep learning applications use dedicated cloud computing services, both for training and model application. For light applications, including scientific machine learning with small datasets or purposes of learning how to use deep learning frameworks, one may often use non-GPU machines as well as laptops. See the notes and references at the end of the chapter for recommended reading of applied deep learning. Large datasets. Deep learning models work exceptionally well in cases where input data has a lot of features, a setting that is loosely called high dimensional. In a more statistical context, a proper definition of high dimensionality is that the number of features exceeds the number of data points. However, in deep learning, such a distinction is not common. Large datasets with many samples are ubiquitous and often critical to the success of deep learning. Large enough and annotated datasets were rarely available prior to the turn of the century, yet in recent time, humanity has witnessed an explosion of the volume of data stored. As a general guide, consider Figure 1.5, which illustrates recent estimated growth of total stored data on Earth. While clearly not all of this data is open, available, and suitable for deep learning models, this trend in total data storage is also characteristic with data available for deep learning storage. So just reading the caption of the figure, an estimate of the trend of total data storage during each year of the second decade of the 21st century. The graph is in zettabytes, where each zettabyte is 2 to the power 70 bytes, or approximately 10 to the 21 bytes. A key example which was pivotal in the success of the field is the aforementioned ImageNet database, which contains nearly 15 million images, where early deep learning models were trained with 1.5 million annotated images out of the total. Another example is the large-scale text models trained on all of Wikipedia, which as of 2022 includes over 55 million pages, with a comprehensive size of almost 20 gigabytes. Up to the turn of the century, such datasets were much harder to come by, were rarely openly available, and disk sizes of most computer workstations were often too small to accommodate them. However, in recent years, the availability of plenty of rich datasets has been pivotal for the success of deep learning. More information on annotations and popular datasets is in section 1.4 below. The Internet, software practices, and open source. In addition to fast computation and the availability of large datasets, the recent success of deep learning was also fueled by new software development practices that evolved around the proliferation of the Internet. Up to the last decade of the 20th century, most software development involved relatively isolated groups working in companies and research groups or individually. As such, there was not much sharing of ideas, information, packages, and modules. However, by the end of the first decade of the current century, global collaborative community practices solidified and eventually resulted in generally free services such as Stack Overflow, GitHub, GitLab, Kaggle, and many more, which today are a natural part of software development culture and data science culture. A key attribute of these new services is that they incentivize individuals and groups to share their ideas and source with the global community. These developments went hand in hand with the growth of the open source ethos, which is shared and respected by many. By the middle of the second decade of the 21st century, as the strength of deep learning became evident, new age collaborative global software practices were already quite mature. The timing of these events greatly helped the deep learning revolution, as it allows thousands of contributors around the globe to develop software supporting documentation and examples suited for deep learning applications. As a consequence, within a period of few years, deep learning software frameworks such as the now popular TensorFlow, PyTorch, Keras, Fast.ai, Flux.jl, and others became available, quickly matured, and are now widely used. By today, new deep learning ideas stemming from research are often published together with open source software. As a consequence, machine learning engineers and other users of deep learning are able to easily and quickly use the state-of-the-art models and methods. All of these practices are key ingredients, not just of deep learning, but of data science and software development at large. However, in terms of deep learning, of the deep learning revolution, the timing of events was just right. Okay, so that concludes section 1.3. I hope you enjoyed the video. Please share comments and feedback below. Thank you.